The SuperSoaker water gun was a revolution in water gun technology. The pump handle is moved back and forth, building up a significant pressure in the water reservoir. The water is released by pulling a trigger and shoots for a significant distance. Assume that one can make an absolute pressure of 8 atmospheres in the reservoir. Find all the following. A, the velocity at which the water leaves the gun. B, the volume rate of flow. And C, the distance that the gun fires if it is held horizontally 1.2 meters above the ground. One hint, the reservoir is to be considered a tank of water in which the water moves with negligible velocity. This is a fluids problem for which we'll use the Bernoulli equation or the Bernoulli principle to solve for all of our unknowns. The style with which one performs a Bernoulli analysis is very similar to that of conservation of energy. In conservation of energy, we select two moments and connect these two moments via the principle of conservation of energy. In a Bernoulli analysis, we pick two locations within the same fluid and connect these with the Bernoulli equation. What we'll be doing in this problem is connecting the surface of the water in the reservoir. We'll call that location 1, since that's where the water begins, to the water as it exits the gun. The Bernoulli principle tells us that the following quantity, pressure plus 1/2 density times velocity squared plus density times g times y, takes the same value at each of the two locations. To be clear about which one we're referring to, we will put a 1 subscript on the pressure, velocity, and y location when considering the tank of water, and we'll put a 2 subscript when we consider the location at which the water exits the SuperSoaker gun. We are told in the problem that at location 1, the absolute pressure is 8 atmospheres. We'll approximate an atmosphere to be 100,000 pascals, so 8 atmospheres is 800,000 pascals. We're also told in the hint that we should neglect the velocity at location 1, and we'll do so, leaving the only other non-zero term at location 1 to be the density of water, which is 1,000 kilograms per cubic meter, times g times the height at location 1, which is 0.08 meters. Numerically, this last term is actually negligible in comparison to the 800,000. However, the problem was designed this way to serve as a reminder to check all three terms at each location: pressure, kinetic energy, and potential energy. Following up for location 2, we recognize that the pressure here should be the same as the air. Whenever two fluids are in contact, they will have the same pressure as each other. Since at this moment the fluid comes in contact with the air pressure of the outside world, we'll label that as 1 atmosphere, which we're approximating as 100,000 pascals. At this location there will be some kinetic energy that we don't yet know. This will be 1/2 the density of water, which is 1,000, times the velocity at location 2 squared. And since we've labeled y equals 0 at location 2, there's no gravitational potential here. This equation has a single unknown, the velocity at location 2, and so we can solve for that, yielding the answer desired for part A of the problem, 37.4 meter per second. In part B of this problem, we are asked to quantify the amount of water that flows out of the SuperSoaker. There are two common ways that one quantifies the amount of water. The first is to take the density of the fluid times the area times the velocity. Looking at the units carefully, you'll find that this gives you kilogram per second as the amount of fluid flowing through a hole. If the fluid is a gas, it's very important to use this quantity, since the gas can be compressed and have varying densities at various locations. However, it is more common when the fluid is a liquid to use the simpler form area times velocity, since area times velocity is cubic meter per second. In our case, we have a radius of 1 millimeter, And so the area of the hole will be pi times this radius squared. And the velocity is the result from part A, which is 37.4 meter per second. This gives us the result 1.17 times 10 to the minus 4 cubic meters per second. Finally, in part C, we're asked that if the water gun is fired horizontally and held 1.2 meters above the ground, where does the water hit the ground? This is a projectile problem. The first thing we recognize is that the 1.2 meters represents the initial height of the water as it exits the gun, and the 34.7 meter per second represents the initial velocity of the water, and since the gun is held horizontally, that velocity is entirely in the x direction, meaning that the velocity in the y direction at the initial moment is 0. To answer the question, where does the water hit the ground, we need to supply a value for the variable x. This is an ill-formed question because x takes a large variety of values as the water travels on its way towards the ground. What we need to do is we need to specify that we want to know the x location when y is equal to 0. That is indeed a well-formed question. However, as we remember from projectile motion, there are no x's in the y equations and there are no y's in the x equations. The only variable that is in common between both the x and the y equations is t. So in order to solve this, we'll have to do two steps. The first step is to find the time at which y is 0. And the second step will be to find the x at time equal to the answer from the previous question. Let's begin with the first step. In order to solve for the time when y equals 0, we'll need the equation that relates y to time. That equation is y0 plus v0y times t minus 1/2 gt squared. Plugging in the values for the constant and recognizing that we need to evaluate when y is equal to 0, we get the equation shown here, whose only unknown is the time, leading us to t is equal to 0.49 seconds. The second step in formulating the solution is to find x at the time equal to the answer. The equation that relates x and time is this one. And using an initial x location of 0, we find the result 18.5 meters.